had more
space
points.
to connect. Used to be they also have these things that you can pull out and they become larger.
That's pretty nice, absolutely.
Yes, you've got type one.
I don't know what happened on the slide that I sent you, because even the one that I previewed on yours was still there, so hopefully it
Maybe it
remains.
was just because I don't have PowerPoints on that laptop I was using, so maybe it was Keynote mangling it something.
Maybe.
But yeah, it was just showing it was completely blank in the one you sent earlier.
Okay, shall I get started?
Yep, whenever you're ready.
Hello, my name is Greg Johnson, and this is my dissertation presentation on measuring explicit congestion notification usage in 2026. So this is a comparative study with a study that was done 10 years ago by Colin Perkins and Stephen McGuiston. They measured ECN capability and deployment over the network, and my research is kind of doing that again, comparing the results and seeing if anything has changed in the past 10 years. So we'll go over my methodology, we'll go over a little bit of background, we'll go over my methodology, and then we'll go over the results that I found and some of the key findings. So a little bit of background. Peter's presentation was actually perfect because it pretty much, mine kind of leads on from there, talking about the same thing of congestion control. So the background is that, as Peter was saying, packet loss-based congestion control is how congestion control works in the network. So when this is a router and this is the incoming traffic and the outgoing traffic, the way that congestion control works is that if a sender is sending to a receiving router too quickly, the queue in the router builds up. As that builds up, packet loss occurs at a certain point once the send rate gets too high, where the router physically, well, maybe not physically, but cannot keep up with the amount of packets that are coming into its router. So upon realizing that it's at its limit, that's when packet loss occurs. The router detects this packet loss and it sends back to the sender that it needs its send rate to decrease in order to be able to actually take in the packets that's being sent. So the costs of this are increased latency, because the packets have to transfer through this queue and the packets are being lost, the latency increases. There's increased buffering in video calls and live video, and there are dropped frames in the same live video and video calls. So the explicit congestion notification is 2 bits in the IP header that are a notification to the sender for it to reduce its send rate. What it means is that when the sender is sending the receiver packets too quickly, the router will have an artificial threshold here, say, where packets after that point are going to be marked with the ECN marking. When the router receives that packet to say, my queue is going to be too full, it is sent back to the sending router, and before packet loss occurs, the send rate is put down, so the throughput of the video and the buffering is greatly reduced. So as I said, it's in the terms of service field. So this is the entire IP header, and the terms of service field is from the 8th to the 15th bit, and it's shared by the differentiated services field, which we'll get onto in a second, because there's a controversy there that this terms of service field has had a history of being stripped by network providers due to the fact that the differentiated services field would actually put packet prioritization, which a lot of ASs and a lot of networks were not too pleased with. And this is how it works. So it's got 4 bits. 00 means that the packet is not ECT friendly, which means ECN capable transport. ECN capable transport 1, ECN capable transport 0 are equivalent, and they both just mean that the negotiations can occur with ECN in mind. And congestion experience is 11, and that just means that's what the router sends to the sender if it's going too quick, if the send rate is too fast. So my research question is a comparative study of explicit congestion notification deployment, measuring ECN adoption after a decade of internet change. So why would I be doing this now? Why is this measurement really important? So UDP, there's not been a dedicated UDP ECN measurement for 10 years. As I said, Colin was the last one to do like a full measurement study of just ECN measurements. The quick protocol depends on UDP. So ECN is critical for reducing latency and packet loss. It has a real world impact, like I said, streaming buffering, live sport dropout, and video call throughput. And ECN historically, it was released in 2001, and it's had a wide implementation, but only moderate use due to the aforementioned stripping that can occur by network providers such as like businesses or exchange points. So our methodology, I decided to go with, for probing servers across the internet, I decided to go with NTP servers, which are network time protocol servers. These are servers that all sync up a universal time. They all calculate the same time, and they all sync that up to the same one, so that anybody can ping one of these servers and get the universal time that all these servers agree on back to its device. So the reason I chose this is a simple UDP and TCP negotiation. UDP, you simply just fire a packet asking for the time, and it fires you back the time, and it will also send you that IP header that I was showing earlier. They're globally distributed. These green crosses represent NTP servers across the world. So as you can see, there are NTP servers, there's high concentrations of NTP servers in the States and in Europe, just due to being more of a developed part of the world. And you can see that as a comparison to the old study, there actually are some more NTP servers appearing across more developed parts of the world, like South America, Africa, and kind of like the China area. And I also chose NTP because it matches the 2015 methodology, which means it's very easy to compare my data. So in total, 2,685 servers were discovered via a week-long DNS pool crawl. I basically just ran a script that would query different NTP pools from different countries, and it would just, basically the script would just run infinitely, so I just kept on running it for a week, and I would, every time you query from a different region, you get a different NTP server back, since they're constantly rotating, which allowed me to get all of these servers. And I used the same, for measuring the actual, the measurement locations that measured the servers, I used the same 9 EC2 regions that the 2015 paper used, plus the addition of Africa and the UAE. I do have some data from the UAE, but unfortunately the server did go down recently due to some conflicts in the Middle East that are going on just now. So, as part of my methodology, the way that the code actually that I ran the measurements is I ran 4 probes per server. I would run a UDP probe, a UDP plus ECN probe, a TCP probe, and a TCP plus ECN probe. And I would also run an ICMP traceroute after each UDP ECN probe to kind of see through ICMP echoes the path that the packets were likely taking. And I also had TCP dumps that captured these ICMP packets, and I also had TCP dumps that would capture the UDP and TCP packets, so I could use them for later analysis of my results. So I captured 170 traces across 11 regions. This flowchart just kind of shows, did you probe all the IPs? No. Send UDP plus ECN, send TCP plus ECN, log the result, did you probe all the IPs, and for 170 traces. So, to get into my results, these are some of the headline results. So UDP reachability with ECN remains pretty consistent with the study I was comparing to. So the top diagram and the bottom diagram, this is my measurements. You can see in dark green the additional regions that I took, and at the bottom I have Colin Perkins and Mickelsen's data in their study. And you can see you're getting mostly over 98% on the results here, and on my results you're getting maybe a little bit higher on the upper end of 99% of results. You can see here that there's a bit of a dropout in Singapore and Tokyo. These readings were taken between the 13th and the 15th of March. So I don't believe, this diagram is servers that respond to not ECT and ECT0 marked packets. So what that means is if it's reading, say, 98%, that means that 2% of the servers are not responding to ECN marked packets, but 98% of the servers are responding to ECN marked packets as well as not ECN marked packets. So we can see that the data is quite consistent with the other study. Even with the days that the packets dropped, they didn't even drop it below 96%, which is still a pretty high reading for UDP reachability. The other graph here that I'm showing, this is slightly different. This is the inverse. So this is servers that responded to ECN marked packets and also responded to not ECN marked packets. And you'll see that these between, if you see this is the first one and this is the second one, you'll see that it's much closer to 100% because this server is showing servers that respond to ECN that also respond to not ECN. If packets to these servers were not to respond to not ECN marked packets, then the NTP servers this wouldn't work because they need to be able to respond to UDP packets first and then additionally respond to ECN like optionally. So the reachability of these is much higher for these results, which is still consistent comparatively with the 2015 results. This diagram shows differential reachability. So what you're looking at in this diagram are these large spikes. These large spikes for this diagram on the left show that servers that respond to respond to not ECN, but don't respond to not ECN. So the servers here, if there's a spike, it's responding to a not ECN marked packet, but it's not responding to an ECN marked packet. So for Collins data, there was about, I believe to be about 9 to 14 servers on average across the not responding to ECN when he measured it. And my data, which is the next part here, slightly less. I was measuring about 6 to 8 servers would not respond to ECN. So there'd be a marginal decrease in the amount of servers that don't respond to ECN, which is a good thing. On the left, the diagram, the same as before, is showing the inverse. So it's showing servers that respond to ECN marked packets, but don't respond to not ECN marked packets. And across every server, it's quite rare to have a server that responds to ECN but doesn't respond to not ECN. As you can see, it's a lot more, with a few spikes which are likely attributed to transient loss and packet loss across the network. These are my TCP ECN results. If you're going to ask me later about the result that surprised me the most about my dissertation, it was definitely my TCP ECN negotiation across the network. I found my TCP ECN support to be significantly lower than McWisson and Perkins in 2015. So I was reaching my data set was reaching more servers. You can see 1,500 servers were being reached for TCP, whereas it was about 1,400 or 1,300 for the McWisson research. But you can see that there's a noticeable decrease with about 800 servers actually being able to negotiate ECN on TCP, and over 1,000 consistently negotiating ECN in the data set in 2015, which I guess we can discuss a little later.
That one's weird. I don't understand it. I would have expected the opposite.
Yeah, no, I would have as well, with the changes to the network and the adoption of ECN increasing. With this graph of trends here, you can see all the prior work measuring TCP across the network, and it seems like it's on a semi-exponential increase to how much TCP can be negotiated, and then you kind of have this outlier result being my 2026 study showing that TCP negotiation has actually kind of dropped significantly from 82% to about 43%, which is quite a surprising result from my measurements that I was not expecting. Another thing that McWisson and Perkins did in their paper was a UDP-TCP correlation. So they were correlating if UDP and TCP servers that did not negotiate ECN had any correlation. And this is their study. In their original study, you can see quite high differences, which kind of insinuates that the correlation between UDP and TCP failing to negotiate ECN was not extremely correlated. It was actually quite different. But you could find in my study that the difference is much lower, with some cases even being 0, which kind of insinuates that the UDP failing ECN and the TCP failing ECN are actually a lot more correlated in 2026, which I thought was a very interesting result from my data set. Finally, just to preface this before we get into the results, a slight oversight in my paper is that Collins' paper used, for tracing the routes that the packets took across the network path, he used UDP packets with ECT markings and captured the ICMP responses. What I did in my paper was I tested both of doing that methodology and also sending ICMP packets with ECN markings, and I was finding much more consistent and much more results reaching their destination addresses when I would mark ECN with ICMP. So these results are not directly comparable because they are showing slightly different things. This is showing UDP, ECT markings and showing the responses, whereas this is showing ICMP with ECN markings across the network. But regardless, you can still see that there's a much more increased amount of ECN stripping in the network, and it seems to be happening at quite early points and then propagating out to the destination addresses. This diagram was plotted with a plotting software called Nito, and for a different kind of view of the exact same data set, I also plotted with a plotting algorithm called 2Pi, which shows much straighter lines, and you can definitely see that there's a few ECN, a few hops in the network here that are probing stripping ECN quite early, and that are kind of propagating down the path where ECN is switched off early and then not switched on later on in the path. So those are my headline results. For my future research, I would like to repeat, or maybe I would not like to, but it would be interesting to see the measurements repeated using the ECT1 marking in the IP header instead of the ECT0 marking. There was some discussion that I saw online that maybe changing that to ECT1 would slightly change the behavior of how middle boxes and ASs were going to treat that marking in the IP header. I'd also be interested to see in enabling the congestion experience marking and measuring how well that actually works across the network, because this study just shows the negotiation of ECN. It just shows the two endpoints are willing to negotiate ECN, but it doesn't go into the actual congestion experience of actually dropping the congestion window, as Peter was kind of talking about in his study of the congestion window actually being dropped. I would like to extend the probing to quick over UDP. There was a really good study done I think 3 years ago, Challenges in the Wilds, which is a quick study showing kind of the same thing of measuring quick connections over the internet using domains instead of NTP servers, which would be an interesting thing to measure again. I would like to repeat the study using IPv6 packets. For the entire time I did this study, I used IPv4. That was just for high comparability, just to compare with the study that I did before, so that was kind of the design choice of why I did that. But I think a future study with IPv6 being much more implemented in the network, it would be interesting to see the result of using that instead of IPv4, because it still has this IPv4 packet here, and you can still see that ECN is be able to be negotiated. And I would like to investigate further the unexpected decline in TCP ECN negotiation that I had. So that's the end of my presentation. These are some of the numbers that I had in some of those graphs that I was showing. And does anybody have any questions?